Here's something you probably saw in Calculus 1 class. Great, I'm glad you're happy about that. Anyway, falling objects. You probably saw this and solved this differential equation with initial conditions. If a projectile is launched with initial velocity v sub 0 from an initial height h sub 0, then the model representing the differential equation whose solution gives the height above ground of the object at time t is given by the initial value problem, the change in the height with respect to time, actually the second derivative, which is the change, actually the second derivative of acceleration is negative g being the acceleration due to gravity, with the initial height at h0 and the initial velocity h prime at v0, with g the acceleration due to gravity. And this is a linear second order equation. Second order because it's got a second derivative in it. But h doesn't occur anywhere else, so it should be an easy one to solve. But if you recall, you probably did this somewhere. Integrating one side, you get dh dt equals negative gt plus a constant, and you could use this to find that constant, and then integrating it again, you would get h equals integrating both sides negative gt squared over 2 plus this constant times t plus this constant, applying your initial conditions. So that is certainly one you've already seen. Moving further with air resistance, and here's where it gets a little bit more complicated.
Oh.
Well, anyway, now that we look at the complicated version, if we further complicate this with air resistance, which is a force acting upward as opposed to downward on the body, that is proportional to the velocity. In other words, the faster it's going, the more force upward from air resistance. And change your orientation so the positive direction is downward now. Then the net force acting on the object is its mass times gravity minus that k, which has to do with the particular object's air resistance. For example, k would be greater if the object had a larger area and less weight. So the air resistance would be higher. Anyway, times the velocity. So here gravity is pulling it downward while the air resistance slows the fall. So gravity pulling it downward, air resistance slowing the fall. The faster it goes, the more air resistance. So it's an added complication that you probably didn't see in calculus class, and matter of fact, your calculus teacher could have possibly ignored it. I know I would. Or could have said, you know, this really doesn't take into account air resistance, and if you do, then you have to get the differential equations to study that. Anyway, Newton's second law is force equals mass times acceleration, and recall acceleration is the change in velocity with respect to time, dv dt. This yields the linear first order equation, mass times acceleration equals force pulling it down minus force pushing it back. And with this, we could do a little integration and solve that one. Actually, that one looks pretty easy to do as a separable equation. But it's also a linear first order, and those are all things in our near future.